In this chapter, we're going to talk about gases. We're going to talk about gas laws, some of which you may be familiar with, some of which may be new to you. And we'll talk about ideal gases. And towards the end, we will talk about real gases and sort of difference between those. So let's first talk about really substances that exist as gases under normal conditions. So when we talk about sort of normal conditions, these are really sort of everyday conditions, room temperature conditions. So typically that refers to a pressure of 1 atm, which is an atmosphere. So atm is obviously a unit of pressure. And the temperature being sort of 25 degrees. So as you go on with your chemistry journey, you'll talk about things that are sort of standard conditions. And these are typically standard conditions. These are typically sort of table conditions where you go look up values in tables and how they're sort of calculated. And they're typically calculated by a temperature of 25 degrees. Pressure is 1 atmosphere, although we're not really talking about solutions in this sort of chapter here, but typically solutions are 1 molar. So these are sort of the standard conditions that we talk about. Now, under these sort of normal standard conditions, ionic compounds typically do not exist as gases under these conditions. And that's because ionic compounds are held together by very strong electrostatic attraction. So obviously ionic compounds are cations, which are positively charged, anions, which are negatively charged. And this attraction, which is really an intramolecular force, is probably one of the strongest sort of forces that you could have. And under normal conditions, really an ionic solid will not really go into the gas phase all that easily. You can pretty much heat the crap out of it and it will not go into the gas phase. We may saw some of that when we did those earlier experiments in the evaporating dish and you evaporated off all the water. You were left with a solid. You can continue to heat that thing. But really what will start to happen before it'll even get near the gas phase is it will start to melt. So kind of look, maybe some of your solids maybe looked like it was maybe starting to melt as you continuously heated it. So we typically don't find ionic compounds in the gas phase under normal conditions because of those really strong electrostatic forces. Now, molecular compounds or covalent compounds where we share electrons are a little bit different. We can find some molecular compounds that are gases under normal conditions. So things like carbon monoxide, carbon dioxide, ammonia, and methane. These are all gases. But a lot of molecular compounds will be liquids or solids under normal conditions. The major difference between sort of an ionic compound and a covalent compound is under normal conditions, you can kind of easily convert a molecular compound into a gas than you can an ionic compound. The prime example that we're all probably familiar with is water. So water, which is a molecular compound, can be sort of easily converted into a gas, and that's what happens when we boil water. When we boil water, right, our liquid water turns into a gas and we get steam that basically happens. And the reason it's really a lot easier to turn something like water, which is a molecular compound, into a gas than say an ionic compound is when we have water molecules, they are polar. Oxygen side more negative, hydrogen side more positive. So what holds these guys together is what is known in this case as hydrogen bonding. And hydrogen bonding is really what is referred to as an intermolecular force. And that is a force that holds basically one molecule together with another. So basically the force that basically holds that one entire water molecule attached to that other entire water molecule is an intermolecular force. For example, within a single water molecule, there are intramolecular forces. And that would be the covalent bond between the oxygen and the hydrogen on both sides there, where they're sharing electrons. Intra meaning within the molecule, inter meaning between two different molecules. We know that usually speaking, intramolecular forces are usually much, much stronger than any intermolecular force. And we know that for the example we were just talking about here, which is water, because when we start heating water, what happens is the bond between the two water molecules is really the first thing that breaks at we hit the boiling point. If it was opposite, and this guy was actually weaker, these bonds, than the intermolecular force, when we would heat it, we'd get alphabet soup, we would get hydrogen gas, oxygen gas, everybody would fall apart, which would not be good if you're trying to make pasta. So that intermolecular force is a lot weaker. So very easily, just by heating something like water, we could break the bonds between the different water molecules, and we could get something to go into the gas phase a lot easier. So the general rule is the kind of stronger the attractive forces between, say, molecules, the less likely that it will exist as a gas. Something like methane, for example, here, that is a nonpolar molecule, which is basically held together with other methane molecules through the weakest type of intermolecular forces, which are known as dispersion forces, which is why methane is a gas. It could go into the gas phase really easily. So a lot of organic compounds, as we might talk a little bit about, they are basically held together by very weak forces. And that's why if you think about a lot of the organic ones that you might know, like methane, propane, butane, those are all gases basically, and they're held together by very weak forces, and they go into the gas phase really easily. That's also why when you take organic chemistry, they throw you in a fume hood, because a lot of stuff that you use in there can go into the gas phase very easily just by kind of opening it up, and it can go into the gas phase. So they keep you in the fume hoods sometimes, or most of the time. So substances that can be found as gases, some of these we should hopefully know. Obviously, a lot of those diatomic elements that we talked about way back when, those guys are gases. So hydrogen gas, nitrogen gas, oxygen gas, fluorine, and chlorine gas. Ozone is also a gas. And then obviously we have our group 8, which are noble gases there. And those are monoatomic gases. So those guys, again, come as basically ones is how they come. So it's our helium, our neon, our argon, krypton, xenon, all of our ons there. So again, under normal conditions, this is pretty much where we find a lot of our gases happen. So some characteristics of gases, obviously in the gas phase, gases assume the volume and shape of their container. And the idea when we do get to the gas phase is everybody has pretty much broken apart from one another. So as they are flying around, they are uniformly filling the container. And as we'll talk about, actually, one of the things that makes something sort of an ideal gas is pretty much that idea, the idea that the volume of the gas itself is negligible compared to the volume of the container it's flying in. So what you'll see is in a lot of problems, when they sort of refer to the volume of the gas, they actually refer to sort of the container at which it's in, with the idea that it's sort of behaving ideally and filling it uniformly throughout. Gases are the most compressible state of matter. Gases will mix evenly and completely when they're confined in the same container. And as we'll talk about in this chapter as well, sort of another aspect of what makes something sort of an ideal gas is the idea that you could have multiple gases together under normal conditions, and they pretty much will almost behave like they are in the container by themselves. So you could have different gases within the same container. And under ideal situations, we assume that really there's no interaction between the different gas molecules that are flying around. Makes some of the calculations a lot easier when we do it. Gases also have a lower density than liquids and solids. So typically when we think about the density of liquids and solids, they're usually in grams per cubic centimeter or grams per milliliter. When we do kind of the density of gases, typically the units are grams per liter. And we're going to talk about calculating the density of gases in this chapter. And those are the typical units that we end up with, which are grams per liter. One of the really most important aspects of a gas is the pressure. And obviously, as the gas molecules are flying around, there's going to be a number of collisions that occur. And the increase in the amount of collisions basically will increase the pressure. So obviously the pressure is related to the number of collisions that occur. And as those increase, we do see an increase in pressure. And as those go down, we do sort of see it come down. There are many units of pressure that we sometimes come across. Pascals is one. Kilopascals is also sometimes used. A lot of people use Newton meters squared there in chemistry. This row of 3 here is sort of the big one that we use a lot, which is 1 atmosphere is equal to 760 mmHg. mmHg is millimeters of mercury, and that equals 760 torr. The relationship between an atmosphere and a Pascal is 1 atmosphere is 101,000 or so pascals. There's other units that we sometimes see, PSI, which is pounds per square inch. We also see a bar is also another unit of pressure that commonly is used. A bar and atmosphere are pretty close to being almost a 1-to-1 relationship. It's like 1.01 to 1. They're very, very close. One of the ways that we do measure pressure is with a barometer, which is what we see over here. And this is a more traditional barometer, which I guess they probably still make, but we don't use a lot in schools anymore because it is traditionally made with mercury. So a traditional barometer has basically a pool of mercury there and kind of a glass tube. And as atmospheric pressure presses down there on the mercury in the tube goes up and down accordingly. Mercury is one of the weird sort of substances, if you will. Not really weird, but it makes an inverse meniscus. So the meniscus actually curves upwards when you're dealing with mercury. You do the same thing, you read it, in this case, actually from the top of the meniscus, if you happen to come across mercury, which I doubt you will here in school. But you actually do read it that way. So that is really where these names come from. That is because on a traditional barometer, even the one we got in the room there, there's a ruler. And a lot of times the ruler is in inches or centimeters or millimeters of mercury. So it's basically where that name comes from. It's basically taking a ruler reading of how high the mercury is in the column. Torr is named after the guy who invented the barometer, Torricelli, and that 760 is an important number. It is a conversion that we use to go between the different units. So if you have atmospheres and you want either torr or millimeters of mercury, you're going to multiply by 760. Or if you have millimeters of mercury or torr and you want atmospheres, you're going to divide by 760. We get the atmospheres. A torr and a millimeter of mercury are basically a 1-to-1 relationship. So if you have to convert between those, pretty simple, just change the units. The number stays the same as it is a 1-to-1 relationship. Any questions on that there? Now, as we go up there from sea level, the pressure obviously changes, right? Which is why they pressurize planes when we fly on them and all those good things. And you can see as we get higher from sea level, the pressure starts to drop as we go higher up. And it does affect things like boiling. It can affect things like boiling points and things of that nature, which we'll talk about in a later chapter. So this is a manometer, which is used to measure the volume of a gas or measure the pressure of a gas. And in this case, it is against a vacuum here, which means it's closed, basically. So we have some mercury in the column. And obviously, as the gas sort of expands in the column, it is going to push the mercury. And basically, you can measure the height there, and the pressure of the gas will be equal to the pressure of the height. If you do it in sort of an open environment here, you do have to take into account the atmospheric pressure that is pushing back down on it. So it would be the pressure of the column plus that atmospheric pressure, which is basically kind of pushing it back down on the other way. So you kind of add that back in to get the pressure of the column. When we talk about sort of gas laws, there's really sort of three variables that we deal with a lot, and that is P, which is pressure, that is V, obviously, which is volume, and that is T, which is temperature. So we're going to see a number of gas laws that obviously deals with each of these sort of variables. In certain cases, we may keep one of them constant while varying the others. And in some cases, we may just vary everybody that is there. But those are the important sort of variables that we deal with. So the first sort of relationship we're going to look at is really sort of Boyles Law. And Boyles Law basically dealt with pressure and volume and held temperature constant in this case. So if we look at sort of the relationship of what happens as we vary the pressure and the volume here, we can see here that our volume is large and our pressure is relatively small. As the volume starts to decrease, we start to see a rise in the pressure indicated by a rise in the mercury. And as the volume gets even smaller, we see a much larger sort of rise in the mercury in the column. So it does make sense if you think about gas molecules, which are constantly flying around. If you take the volume basically and squish it together, pretty much they don't have a lot of room to fly around in. That's going to increase the number of collisions. And as it increases the number of collisions, it will obviously increase the pressure. If you increase the volume, you give everybody a little bit more room to fly around in. And because they have more room to fly around in, that's going to cause the collisions to start to come down. And you will also see the pressure start to come down. So Boyles Law basically is that relationship that the pressure is proportional to 1 over the volume. Frankly speaking, that means as the pressure goes up, the volume goes down, and vice versa. As the pressure goes down, the volume goes up in this case. If you take any gas observing sort of Boyles Law situation, you could take a pressure times a volume measurement for the gas, and it will always come to a constant value. So if you take any pressure times volume sort of pair of measurements, it will always come to the same number. And that is why in this type of gas law here, we can basically set them equal to each other, and we get kind of like a before and after type of situation where we have Boyles Law is P1 times V1 equals P2 times V2. This again is at constant temperature. And that's what we see here at a much larger volume. We have less pressure. At a smaller volume, we have more pressure. And that is the linear relationship that we get. Pressure is equal to 1 over the volume. It's really important a lot of times to try to understand the relationships that you see in gas laws, because it's very common. Sometimes people make mistakes where they inverse numbers or reverse numbers, do like a V2 for V1 or a P1 for P2 and kind of flip numbers around. So if you understand sort of the relationship, it can help you make sure that the answer you get, does sort of make sense when you do it. So why don't we try one here? A sample of chlorine gas occupies 946 milliliters at a pressure of 726 millimeters of mercury. What is the pressure if we change the volume to 154? Let's take a moment or two and see what you come up with here. And we have a volume of 154 milliliters in this case. Now, remember that in terms of volume and the units, they can really be any units you want as long as they are obviously the same on both sides, so everything cancels. And really the same thing for the pressure. The pressure could be any units you want as long as, again, they are really the same on both sides. So we could just call the first ones here 1s, second ones 2s, and That would give us P1 V1 is equal to P2 V2. In this case, we're going to divide the V2 to the other side. That gives us P1 V1 V2 equals P2. Putting our numbers in, 946 milliliters, 726 millimeters of mercury divided by 154 milliliters. Milliliters will cancel, going to leave us in millimeters of mercury, and that's a 946 times the 726 divided by a $1.54. We'll call it 4460. The units here will be milliliters, as obviously, I'm sorry, millimeters of mercury, as that is our pressure there. Question on that calculation. So once again, we could kind of look to make sure, it sort of makes sense. Here we are looking at our volume going down as it started at 946, ended at 154. That means that our pressure should go up. Started at 726 and it definitely went up. So again, we did obviously move in the correct direction. So it's a good way to sort of think about it and check yourself. Any questions on that there? All right. Try another one here. The inflated balloon is 0.55 liters at sea level, rises to Boyles Law here. And again, we could call these guys ones and twos. In terms of units, this is an atmospheres and that's an atmospheres, which is good. This will be liters, which means we'll just end up solving for liters at the end. So P1 V1 is equal to P2 V2. In this case, we're going to take the P2 to the other side. That will give us P1 V1 P2 equals V2. And we end up with 1 atmosphere times 0.55 liters divided by 0.4 atmospheres. Atmospheres here will cancel. And we'll end up with 1.4 liters at this point. Any questions on that one there? Once again, we could kind of check to make sure everything is going right. We have a pressure that is decreasing. That means our volume should be increasing. And it went from 0.55 to 1.4. So again, it is moving in the correct direction at least. Question on Boyles Law here. Yeah. The volume's increase. Yeah, so it's a good chance. It's a good thing to sort of check your answers just to make sure it makes sense. For example, here, if you calculated something that ended up being less than 0.55, then definitely going in the wrong direction based on how Boyles Law should work. So probably maybe inverted some numbers, which is a common mistake people make in gas law problems. They gotta put things on the wrong side. Other questions? Yeah. No? All right. The next sort of laws we're going to talk about are sort of two laws, which is Charles Law and Gay-Lussacs Law. So Charles Law and Gay-Lussacs Law. And Charles Law dealt with volume and temperature relationships, holding pressure constant. While Gay-Lussacs really dealt with kind of pressure and temperature relationships, holding volume constant. So basically, Charles' law is, as we will see, V1 over T1 is equal to V2 over T2. While, and again, this is at constant pressure. And Gay-Lussacs law is kind of really P1 over T1 is equal to P2 over T2. And this is at constant volume. So let's talk a little bit about what will happen sort of in each of these situations and, how sort of volume and temperature change and pressure and temperature change. Let's start with on the right-hand side, sort of Gay-Lussacs law. If we increase the temperature in this case, we would expect the gas molecules obviously to pick up the energy, and they should start moving slower or faster. They should start moving a lot faster, right? As they increase temperature, they gain energy, they're flying around a lot faster. In the case of Gay-Lussacs, pretty much the volume is locked into place. It's rigid, it will not move, it will not adjust, which means because the volume is pretty much going to be constant, and we have gas molecules that are flying around a lot faster when we increase the temperature, we're going to definitely see a lot more collisions that's going to occur, and we should see actually the pressure start to increase in that case. And that is what we will kind of see is actually an increase in pressure as you increase the temperature. Opposite would be sort of true here in this situation. If we lower the temperature, that means our gas molecules are going to be flying around a lot slower. And once again, the volume is not going to adjust or anything like that, which means it's going to take longer for collisions to occur. And longer for collisions to occur means that we will start to see the pressure come down. So in Gay-Lussacs sort of situation here, as the temperature goes up, we do see the pressure go up as well. And as the temperature goes down, we do see a drop in pressure accordingly. Now, when we get to sort of Charles' law over here, where we have constant pressure, but the volume is not fixed, the way it's able to sort of maintain the pressure is by actually adjusting the volume. So when we have Charles' law, what happens is as we increase the temperature, much like we saw over here, we will have gas molecules flying around a lot faster. The difference is in Charles' law is the volume is not fixed. The volume will adjust. And as the volume adjusts, what that allows it to do is give everybody a lot more room to fly around in. And what that does is it keeps the number of collisions basically constant. And thus, that is how it keeps the pressure constant in this case. So what happens is as we increase the temperature in the Charles law situation, we will also see the volume increase to maintain the constant pressure. And vice versa happens. Once again, if we drop the temperature, we will have gas molecules flying around a lot slower, which means on the right-hand side there, we would start to see the pressure start to drop. So what happens in this case is the volume gets smaller. And as the volume gets smaller, even though those gas molecules are moving slower, it's going to allow the number of collisions basically to remain constant. And what we will see is a constant pressure occur. So in Charles' law situation, as the temperature goes up, the volume will adjust accordingly to keep the pressure constant. And as the temperature goes down, the volume will also adjust down to keep the pressure constant as well. Any questions on any of those there? And that's what we see here at a lower temperature. We have a sort of smaller pressure. And as a higher temperature, obviously the volume starts to increase. So lower temperature, lower volume, and higher volume at a higher temperature. Now, one of the aspects of this law, Charles' law and Gay-Lussacs law, is this: if you were to graph volume versus temperature for any gas you like, and do a little plot and extend the plot all the way back to the temperature line, every single gas will hit the magical number of minus 273.15 degrees Celsius. That number should look familiar to you because that is the number we use to do what? Really convert to Kelvin. And Kelvin recognized this and said that that was absolute zero, because when we add 273.15 to convert it into Kelvin, you get 0 Kelvin, which is absolute zero. So the joy of that is, if it is a gas law, the temperature needs to be in Kelvin, pretty much. So pretty much a safe bet that any gas law that you have, including these ones that we just talked about, it needs to be in Kelvin. So our Charles law, V1 T1 equals V2 T2. Temperatures need to be in Kelvin. And our Gay-Lussacs P1 T1 equals P2 T2. Also temperature needs to be in Kelvin. And like I said, pretty much a safe bet if you're doing gas law temperature definitely needs to be in Kelvin. Even in problems where they try to trick you by giving you the temperature in Celsius and asking you to give the answer in Celsius, people go, well, they give it to me in Celsius. I want to give the answer in Celsius. I could leave it in Celsius. You cannot. You got to convert it to Kelvin, put it into the gas law, and then convert it on the back end. So that's a common sort of textbook question. They kind of give you Celsius, so people think you could leave it that way. Now, in terms of the volume or the pressure in either one of those sort of formulas, they really can be any unit you want, again, as long as they're the same on both sides, and the units will cancel. So you can use any unit of pressure in this one or any unit of volume as well. Any questions on that there? Yeah. I personally do 273, which most people do. So that is, again, obviously temperature in Celsius plus 273 is good. Yeah. Yeah, if you want to leave the 0.15, you can, but honestly, most of the time it gets rounded off anyways, and most people use 273, so 273 is still good in this case. Other questions? All right, so let's try one here. Sample carbon monoxide has oxygen. Okay, let's take a look here. So once again, if we kind of pull out the information, we got a volume of 3.2 liters. We also have a temperature of 125 degrees Celsius. We're looking for a final temperature here, and our volume is 1.54 liters. So now we have a few different ones to choose from. We could clearly see there's no mention of pressures, so clearly none of those guys would be good. And you can kind of see Charles' law there. Again, we could kind of put these guys as ones, these guys as twos. In terms of the volume, we're good. They're both in liters, so we don't have to worry about units there. But like normal, we do need to worry about our temperature. So we're going to add 273 to our temperature. That will give us 398 Kelvin. That gives us V1 T1 equals V2 T2. As you may know, if you move across an equal sign, right, everybody ends up in opposite locations, right? Or basically multiplying and dividing is what we're doing there. So we do want to solve for T2, which means we've got to kind of move that guy to the other side. Gives us V1 T2 T1 is equal to V2. We then will move this guy there and that guy there. Gives us T2 is equal to V2 T1 and V1. That's sort of the quick way to rearrange, right? But you're basically multiplying and dividing basically to the other sides. We're going to put our guys in here. This again will give us actually V2 up on top. That will give us T1, which is 398, and our V1, which is 320. Liters will cancel, gets us 154 divided by 3.2. This is about 192 Kelvin would be the answer here. And again, we're looking for Celsius since I asked for that, which means we would subtract 273, and that will get us negative 81 degrees Celsius in this case. 192. Any questions on that there? We could look at our relationship again to make sure. Here we see the volume goes down, which means we should see the temperature go down as well. And that is what we see. If we want to look at Kelvin, it goes down. And obviously Celsius, it goes down as well. Any questions on that particular one there? Okay, so let's try another one here. In experiment, 452 milliliters of a gas in a light bulb. It goes from 22 to 187 degrees Celsius. What is the final volume? Looking out at you there. We got to do our normal sort of temperature conversions, which is adding our 273 to both of these guys. That's going to give us, I think, a 460 over here. And a 295 over here. We could leave our volume in milliliters. Just means when we get the answer, obviously it will be in milliliters as well. That's going to give us a V1 T1 is equal to V2 T2. In this case, we're looking for V2, so we're going to send T2 to the opposite side there, and that would get us V2 is equal to V1 T2 T1. Putting in our numbers, obviously in the right location here, gets us 452, our second temperature up on top, and our first temperature there on the bottom. Kelvins will cancel, once again going to leave us with milliliters. That's going to give us a 452 times 460 divided by 295. Go with a 705 milliliters. Question on that calculation there. Once again, if we kind of look at it here, we see our temperatures increasing. So we should see an increase in volume. And again, we do going from 452 to 705. So again, that makes sense. Any questions on that one? All right, one last one here in the run. Argon is used in certain light bulbs. We got one that is 1.2 atmospheres at 18 degrees Celsius, heated to 85 degrees Celsius. What is the final pressure here? 2 atmospheres. That goes with a temperature of 18 degrees Celsius. Going to change the temperature there to 85, and we are looking actually for our pressure. So in this case, the one that does fit would be Gay-Lussacs law. P1 T1 is equal to P2 T2. In this case, once again, we're going to do some conversions here on our temperature. So we got a 273 plus an 18. Gets you 291 Kelvin, and an 85 and a 273 gets you a 358 Kelvin. So here we will go 1s and 2s. It really doesn't matter as long as you keep the numbers together, or it doesn't really matter which ones you call 1s and 2s. P1 T1 equals P2 T2. Here we're going to send this guy to the other side so we could solve for P2. Basically multiplying to the other side gets us P2 is equal to P1 T2 T1, giving us 1.2 atmospheres, 358 Kelvin divided by 291 Kelvin. Kelvins cancel, leaves us with atmospheres. 1.2 times 358 divided by a 291er, going to get us a we'll call it 1.48. And that would be atmospheres as we are looking for a pressure. Here we see that the temperature went up, so we would expect the pressure to go up, and it did as well. So we're all good in terms of that. Any questions on any of those there? Okay, so rolling through our never-ending gas law journey here. Next we're going to talk about Avogadro's law. Our good friend Avogadro, he had a number, but he really wanted a gas law as well. So Avogadro, when we think of Avogadro, that is 6.022 times 10 to the 23 is equal to a mole. Yeah. So not surprisingly, his gas law actually deals with moles and volumes. And it is V1 over N1 equals V2 over N2. And this is actually at 2 situations, constant temperature and pressure, where N is the number of moles of the gas. So N is for moles of our gas at constant temperature and pressure. So Avogadro's law, you could use, obviously, like any other gas law. You can plug and chug into there if you got 3 of the 4 and solve for whatever is missing. Another sort of relationship where the idea of Avogadro's law sort of comes into play really nicely is when you are doing gas stoichiometry. And if you are under constant temperature and pressure, It actually allows you to do really stoichiometry using volumes of the gases, just like you would do with moles of the gases. So it could kind of shortcut some calculations sometimes that you would not necessarily have to use a Gauss law in the stoichiometry problem. So for example, as we've seen before, we could say 3 molecules, 1 molecule, and 2 molecules. We also could have the mole to mole relationship of 3 moles to 1 mole to 2 moles. And if this was done under constant temperature and pressure, we could actually use these as volumes, 3 volumes to 1 volume to 2 volumes. Or you could use units like 3 liters to 1 liter to sort of 2 liters in there. So it allows you to sort of do a stoichiometry problem when you're at constant temperature and pressure, using really the coefficients as the volumes of each of those things. And again, like I said, what that actually does is sort of shortcuts a need to use an actual ideal gas law in the stoichiometry problem that involves the gases. So for example, here, if we have ammonia burns in oxygen, how many volumes of NO are obtained from 1 volume of ammonia? So for example, from this equation here, we could actually come up with a bunch of stoichiometry related to this. We could say that there are 4 liters of NH3 for every 5 liters of O2. We could also say for every 4 liters of NH3, we get 4 liters of NO. For every 4 liters of NH3, we get 6 liters of H2O. And obviously you could do it for everybody there, just like you would do a mole to mole relationship. So in this particular case, we want to know if we had, say, 1 liter of ammonia, how many liters of NO would we get? So we could use the relationship just like we would do in a mole to mole relationship and find it between NH3 and NO, which is right here. And just like what we would do with stoichiometry, and by the way, those numbers come from the coefficients, just like you do in stoichiometry, we could really just do a stoichiometry calculation using liters. And we could say for every 4 liters of NH3, you get 4 liters of NO. These guys cancel, and you would end up with basically 1 liter of NO in this case. You could do it for anybody else, if you're interested, say, in water, for 1 liter of NH3. You could use the relationship from the equation and do a little stoichiometry. 4 liters of NH3, 6 liters of water. Liters of NH3 would cancel. 6 divided by 4 gets you 1.5 liters of water would be produced. So one of the added benefits is sort of Avogadro's law, and it does need to be obviously under these conditions of constant temperature and pressure. It allows you to kind of do stoichiometry problems relatively quickly using the coefficients as volume. You could still do this, as we'll talk about stoichiometry problems later on in this chapter, traditionally with gas laws, but it kind of shortcuts it, and you could kind of get it done a lot quicker. Any questions on that there? All right, so taking together all of the gas laws there and some of the ones that we talked about Boyles Law and the relationship between pressure and volume. So as one goes up, basically the other goes down. We also talked about Charles' law. Again, as the volume decreases, so does the temperature, and the pressure will remain constant in that case. And as the temperature increases, the volume will adjust to maintain the constant pressure. Obviously, in a Gay-Lussacs situation where the volume is fixed, like what we got going on down here, again, with that increase in temperature, you will see an increase in pressure because the volume will not adjust to fix it. And as you lower the temperature, you'll see a decrease in the pressure, again, because the volume will not adjust to fix it. Taking Avogadro's law, which, as you can see, volumes of moles are pretty much proportionally related to each other. Putting all these guys together, and their relationships gives us the granddaddy of them all there, which is the ideal gas law, which is PV equals nRT. Now, the ideal gas law is different than obviously a lot of the gas laws that we've talked about up until this point. There really is no sort of before and after, so there's no like two pressures, two volumes, anything like that. It's sort of a one and done situation. It is also the most restrictive in terms of units. So when you use the ideal gas law, everybody needs to be in the proper units. And for pressure, those units are atmospheres. So if you use the ideal gas law, you need to have maybe pressure in atmospheres. You need to also have your volume in liters. N should be moles, or something is wrong. T should be temperature, which is Kelvin. And really the reason for all that is R. R is the gas constant, and R has a value of 0.08206, and it has units of liters times atmosphere divided by Kelvin times mole. So because the gas constant has those units, in order for everybody to cancel out correctly, everybody else needs to be in those units. The good news is you're oftentimes given R with those units. So in case you ever forget, you can just look at it and know what units everybody needs to be in. A lot of people these days use 0.0821. That's okay as well. I use the other number because they beat it in my head and I can't get it out. But, you know, nowadays a lot of books and stuff will use 0.0821, which is sort of the rounded number of it. So also in terms of R, there are different values. There are different values for R. Yeah, there are different values for R, but this is the one obviously that we use in the gas law, the ideal gas law. Bless you. There's a value of R that involves energy, like 8.314 joules per Kelvin per mole, which is not the one you would want to use in this case, unless you want to do a lot of conversions. Now, in terms of R, they typically don't give it to you in problems. They just assume that you know you have R. So that's, again, just a value that you should know and know that you do have it available to you. Another couple of important relationships is standard temperature and pressure. That is STP. When they say at STP, they're actually giving you values. The temperature value at STP is 273 Kelvin, and the pressure is 1 atmosphere, or basically 760 torr, or millimeters of mercury. Sometimes people will see STP in a problem and go, I don't have a temperature or pressure, but they are actually giving you those values basically when they tell you STP. There is a really nice relationship that occurs at STP conditions, and only at STP conditions. 1 mole of any gas will equal 22.414 liters. So this conversion is a nice one that you could use if you are at STP conditions, which means your temperature needs to be 273 and your pressure needs to be 1 atmosphere. If neither one of those or either one of those is not those values, then you should not use that conversion. You should use the ideal gas law. So the benefit of this conversion is sometimes it can allow you not to need to use the ideal gas law, and you can kind of just use this conversion, but you should, again, only use it at STP conditions. The nice thing about the ideal gas law is, frankly, it is a universal gas law, which means you can use it at pretty much any conditions. So you can use it at STP conditions. The ideal gas law, you just put the numbers in, 273 for the temperature, 1 atmosphere for the pressure, or you can use it at non-STP conditions. So when in doubt, roll with the ideal gas law. You would probably get the answer correct. But again, only STP on this condition. That, by the way, is how we get to the value of the gas constant. If we rearrange the ideal gas law and solve for R, put in our values at STP, which is 1 atmosphere, 22.4 liters, 1 mole, NR 273. That is pretty much where our 0.08206 value, 5.43 liters, and we have a temperature of 69.5 degrees Celsius. Once again, you can kind of see the ideal gas law in there. And obviously, we don't have 2 pressures or 2 volumes, which would work with any of the other ones. We do need to do a couple or one conversion at least to add 273 here to our temperature, 342.5 Kelvin. So this give us PV is equal to nRT. In this case, we are looking for pressure. We're going to send volume to the other side by dividing by it. Gives us the pressure is equal to nRT over V. Putting in our moles 1.82. Again, the gas constant, which you always have available to you. And our temperature, which obviously we do need to convert to Kelvin, all divided by our volume, which is 5.43 liters. Liters on top and bottom cancel, Kelvin cancels, moles cancels, leaves us just atmospheres left over, which is good since we're looking for a pressure. 1.82 times 0.08206 times 342.5 divided by 5.43, going to give us 9.42 atmospheres as our pressure in this case. Any questions on that one? Variations of this is very commonly you're given things in grams, so converting grams to moles is done a lot in here, obviously using the molar mass like we've done before. Any questions on that one there? All right, so I want to try this one. What is the volume in liters that's occupied by 49.8 grams of HCl at STP? So hydrogen 1.008 and Cl 3545.